In Lesson 4A, you'll be looking at writing equations from patterns. You'll learn to look for a pattern and write an equation given some of the solutions. Why is writing equations from patterns important in science? Water is one of the few substances that expands when it freezes. The table shows different volumes of water and the corresponding volumes of ice. The relation in the table can be represented by the graph. Let W represent the volume of the water and C represent the volume of the ice. When the ordered pairs are graphed, they form a linear pattern. It looks like a line. This pattern can be described by an equation. It looks like every time the water volume is going up by 11, and every time the water volume goes up by 11, the ice volume goes up by 12. 12 is more than 11, not a whole lot, but enough to notice the difference. A very useful problem-solving strategy is look for a pattern. When you make a conclusion based on a pattern of examples, you're using inductive reasoning. Recall that deductive reasoning uses facts, rules, and definitions to reach a conclusion. For our first example, they ask us to study the pattern and then draw the next 3 figures in the pattern. So our filled-in triangle is in the upper right, upper left, bottom, upper right. So it looks like it's moving around the triangle in a counterclockwise direction. So continuing counterclockwise, we would shade number 5 here, 6, and 7. For part B, they ask us to study the pattern and draw the 17th triangle in the pattern. Well, I don't want to keep drawing these triangles till I get to number 17. So we already looked at the pattern. It repeats after 1, 2, 3, and then is back again to 1. So every third triangle is going to be this. So that would be 3, 6, 9, 12, 15 would be like the number 3. So 16 and 17 would look a lot like number 2. In fact, it looks exactly like number 2. We just should write the number 17 under it, but that's what it would look like. For example 2, they want us to find the next 3 terms in the sequence. Well, how can we get from -3 to -1? I guess we could add 2. Adding 2 would only give me 1. I have to add 4, and I have to add 6. Aha, I see a pattern. I'm adding 2 more each time. I'm adding the next consecutive even integer. So after 9, I'd have to add 8. So I'd get 17. And then I would add 10. So I'd get 27. And then I'd add 12, and I'd get 39. The table shows the number of miles driven for each hour driving. So in 1 hour, they drove 50 miles, 2, 100, 3, 150, 4, 200. Graph the data. What conclusion can you make about the relationship between the number of hours of driving each and the number of miles driven M? I am trying to provide graphs on your lesson paper for these because it makes it easier if you have a scale already set up. So they made their vertical scale going by 50s instead of 1s and plotted the points. And what conclusion can you make about the relation between the number of hours driving and the number of miles driven? Well, it sure looks like it is a linear equation. It's going up. Every time we drive another mile or hour, we drive another 50 miles in distance. So if we go up 50, it'll make us go over 1 hour. 1 more hour of driving, 50 more miles. For part B, they want us to write an equation to describe this relationship. Okay, we saw on the graph that every time we increase by an hour, we increase by 50 miles. So if I wanted to find out the miles, all I have to do is take the number of hours driven times 50. And it looks like it works for all 4 of those points. 1 times 50 is 50, 2 times 50 is 100, 3 times 50, and 4 times 50. If we wanted to write that in function notation, we could write f of h equals 50h. Now they ask us to write an equation in function notation for the relation graph below. It'd be nice to have the ordered pairs written out instead of just the graph. So we have the points, 1, 1. It's an odd scale because they did a vertical scale going by 2s. 2, 4, 3, 7, 4, 10, and 5, 13. So every time x goes up by 1, y goes up by 3. Well, if we try our theory, every time I put in 1 for x, I am getting 2 off of what I want. So the y is always 2 less than 3x. Well, that's not difficult to fix in an equation. So we could just write y equals 3x minus 2. Oh, but wait, they said to use function notation. So I just need to write f of x instead of y. Not a big fix. When writing equations from patterns, we need to look for a pattern in the data. If the relationship between the domain and range is linear, the relationship can be described by a nice linear equation.